There is a moment when you first truly understand it that feels less like learning and more like discovering that something you trusted without question was never quite real. Not a dramatic revelation, not a sudden shock, just a quiet, unsettling shift. The kind that happens when the universe reveals, without ceremony, that it has been keeping a secret in plain sight. If this kind of question keeps you up at night, the kind that starts with a single planet and ends somewhere you didn't expect, consider subscribing. And if what you're about to hear stays with you, a like helps more people find their way here. Look up at the night sky on a clear evening, far enough from the city that the stars have room to breathe, and you will see Venus before almost anything else. It is the brightest natural object in the sky after the sun and the moon. Ancient astronomers called it the morning star and the evening star, believing for a long time that they were two different objects, one that heralded the dawn, one that followed the dusk, before realizing that both were the same brilliant point of light, moving in a slow, faithful arc above the horizon. The Babylonians tracked it with extraordinary precision. The ancient Greeks named it after the goddess of beauty and love. The Maya built entire architectural alignments around its movements. For most of human history, Venus was a symbol of constancy, of elegance, of the universe operating exactly as it should. That story did not survive the 20th century. When we began pointing instruments toward Venus with enough precision to actually measure its rotation, the data that came back was, at first, assumed to be wrong. The radar signals bounced off the planet's surface told researchers something that contradicted one of the most fundamental patterns in planetary science, something so basic, so deeply embedded in our understanding of how solar systems form and function that the initial instinct was to check the equipment, re-examine the methodology, look for the error. The error was not in the equipment. Venus rotates in the opposite direction to every other planet in the solar system. Every planet, Mercury, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, rotates in what we call a prograde direction, counterclockwise, when viewed from above the sun's north pole. This is not coincidence, and it is not arbitrary. It is the direct consequence of how the solar system was born. Roughly 4.5 billion years ago, a vast cloud of gas and dust, a nebula, began to collapse under its own gravity. As it collapsed, it began to spin. Conservation of angular momentum, one of the most ironclad laws in physics, ensured that as the cloud contracted, it spun faster, and as it spun, the matter within it flattened into a rotating disk. The sun formed at the center. The planets condensed from the disk around it, and because they formed from material that was already rotating in a shared direction, they inherited that rotation. All of them. This is not a complicated story. It is one of the cleanest and most elegant narratives in all of astrophysics. A cloud rotates, a disk forms, planets spin in the direction of the disk. The angular momentum is conserved, distributed, passed down like a birthright across billions of years and billions of kilometers. And then there is Venus. Venus does not merely rotate in the wrong direction. It does so with an almost ostentatious slowness that compounds the strangeness. A single Venusian day, one complete rotation of the planet on its axis, takes 243 Earth days. To put that in terms that the human mind can actually hold, while Venus completes a single rotation, Earth has gone around the sun once, and then some. Venus takes longer to spin once than it takes to complete an entire orbit around the sun. Its day is longer than its year. Sit with that for a moment. If you stood on the surface of Venus, setting aside, for now, the 465-degree heat, the crushing atmospheric pressure, and the sulfuric acid rain, you would watch the sun rise slowly in the west. It would crawl across an orange, cloud-choked sky over the course of months. And then, with agonizing patience, it would set in the east. Everything reversed, everything backwards, an entire world turning against the grain of the solar system on a timescale so extended it barely registers as motion at all. This is the first layer of the mystery, and it is strange enough on its own. But Venus does not stop there. Here is what makes this genuinely puzzling, rather than merely unusual. Venus is also almost perfectly upright. Most planets have axial tilts, the angle between their rotational axis and the perpendicular to their orbital plane. Earth's axial tilt is 23.5 degrees, which is why we have seasons. Mars tilts at about 25 degrees, Saturn at 27. Uranus, famously, is tilted at 98 degrees, essentially rolling along its orbit on its side. These tilts are, in most cases, the legacy of ancient collisions and gravitational interactions. They are evidence of a chaotic past, of a solar system that was not always the orderly arrangement of worlds we observe today. Venus has an axial tilt of just 3 degrees. It is almost perfectly vertical, almost perfectly perpendicular to the plane of the solar system. Now, if you are thinking carefully, this creates a problem with the most intuitive explanation for the retrograde rotation. The obvious first guess, the one that most people land on immediately, the one that feels satisfying and clean, is that Venus was hit, that at some point in its ancient past, a massive body struck it hard enough to reverse its spin. Impacts do extraordinary things to planets. The Moon almost certainly exists because a Mars-sized body struck the young Earth and flung enough material into orbit to coalesce into a natural satellite. Uranus's extreme axial tilt is most likely the result of a violent ancient collision. Impact is the solar system's most honest biography, written in craters and tilts and irregular moons. But here is the problem. If a collision large enough to reverse Venus's rotation had occurred, it would almost certainly have also disturbed the planet's axial tilt. You cannot transfer that much angular momentum to a planet without also knocking its axis out of alignment. The physics simply does not cooperate. Yet Venus sits there, nearly upright, spinning backwards, with a serenity that does not look anything like the aftermath of a catastrophic ancient impact. Something reversed this planet's rotation. Something did not disturb its tilt. These two facts are difficult to reconcile, and the attempt to reconcile them has led planetary scientists into increasingly deep and unfamiliar territory. There is another layer to this, and it involves time in a way that human intuition struggles with. We tend to think of the solar system as static, fixed. The planets have been where they are, doing what they do, for as long as anything has mattered. But 4.5 billion years is a duration so vast that it renders almost any change possible, provided only that it operates consistently and patiently. The same force that carves the Grand Canyon over millions of years can, given enough time, reshape a planet's rotation entirely. And one of the forces that has been operating on Venus since the beginning, quietly, invisibly, with no drama whatsoever, is the gravitational pull of the sun acting not just on the planet's solid body, but on its atmosphere. Venus has an atmosphere that is approximately 90 times denser than Earth's. 90 times. The atmospheric pressure on the Venusian surface is equivalent to being 900 meters beneath the ocean. This is not an atmosphere in any recognizable terrestrial sense. It is an enormous, crushing shell of superheated carbon dioxide and nitrogen that envelops the planet completely, moving in complex, continent-scale waves driven by solar heating and gravitational forcing. And that atmosphere, according to research published in Nature Astronomy in 2021, led by Alexandre Correa and his colleagues, may be the very mechanism that turned Venus around. The gravitational pull of the Sun creates what are called atmospheric tidal bulges in Venus's thick air, enormous, slow-moving concentrations of pressure that lag slightly behind the Sun's position as the planet rotates. These bulges exert a torque on the planet itself. Meanwhile, the solid interior of Venus experiences its own tidal friction, a separate force pulling in its own direction. The final rotational state of Venus, the models suggest, is the result of these two competing forces, solid tidal friction and atmospheric tidal torque, reaching an equilibrium over billions of years. Not a collision, not a single catastrophic moment, just physics, operating continuously and patiently across geological time, grinding the rotation of an entire world down and redirecting it. This is a remarkable idea, but notice what it requires. It requires Venus to have had an exceptionally thick atmosphere from very early in its history, which means the thickness of the atmosphere is not merely a consequence of Venus's current state, it may have been a cause, a contributor to the very dynamics that reversed the rotation. And the question of where that atmosphere came from and why it is so dramatically different from Earth's, despite the two planets forming from almost identical material in almost identical conditions, is a question that planetary science has not yet answered to anyone's complete satisfaction. One mystery does not resolve into a solution, it resolves into a deeper mystery. This is, it turns out, the defining characteristic of Venus. There is something psychologically interesting about what happens when you encounter a fact like this for the first time. The retrograde rotation of Venus ought to feel like an isolated anomaly, a quirky footnote in the catalog of solar system oddities, sitting alongside Uranus's extreme tilt and Mercury's unusual density and Saturn's inexplicably beautiful rings. Interesting, certainly. Worthy of investigation, of course, but not something that should fundamentally alter the way you think about the world you live on. And yet, the more you follow this particular thread, the more it refuses to remain isolated. The retrograde rotation connects to the thick atmosphere, which connects to the extreme surface temperatures, which connects to the question of why Venus, a planet that is, by every measurement of mass and composition, essentially Earth's twin, is currently the hottest planet in the solar system, hotter even than Mercury, despite being twice as far from the Sun. These connections form a chain, and the chain, when you follow it far enough, leads somewhere that is considerably more unsettling than an interesting astronomical footnote. It leads to the question of whether Venus, early in its history, looked something like Earth, whether it was, for a time, habitable, whether the process that created its thick retrograde-inducing atmosphere was also the process that ended whatever conditions might have once existed there for something more complex to emerge. But that is a door that opens onto a different kind of vertigo, and one that belongs to a later chapter. For now, stand at the beginning. Stand at the simple, impossible fact. A planet formed from the same cloud of material as every other planet in this system. It inherited the same rotational momentum from the same collapsing nebula. It grew in the same direction, condensed under the same physics, followed the same rules, for a while at least. And then, at some point in its 4.5 billion-year history, something changed. Whether it was a single violent collision or the slow, patient grinding of atmospheric forces over geological timescales, the result is the same. Venus turned around, and it has been turning backwards ever since, slowly, silently, barely moving at all, by the standards of a world in motion. If you go outside tonight and find Venus low on the horizon, brilliant and unwavering, the way it always is, the way it has been for every human civilization that ever looked up at the sky and tried to make sense of what they saw, there is something worth remembering. That light has been traveling through space for a little over 2 minutes to reach your eye, and the world it comes from, the world that has been regarded since antiquity as a symbol of beauty and constancy, is rotating in a direction that defies the logic of its own creation. The solar system has rules. Venus chose not to follow them. Or perhaps, and this is the possibility that should sit with you as this story continues, Venus had no choice at all. Perhaps the forces that reversed it were inevitable, given the conditions. Perhaps the same conditions, operating differently, could have reversed any planet. Perhaps they still could. That, too, is a question for later. For now, the mystery is simply this. Something turned Venus around, and we are not entirely certain what. Every answer we have brings a larger question with it. Every explanation requires an explanation of its own. And somewhere beneath all of it, beneath the atmospheric tides and the ancient impacts and the improbable axial stability, there is a story about this planet's past that we have not yet been able to read. Because Venus, in addition to everything else, has done something rather inconvenient. It has erased most of its own history. The human mind has a deep, almost biological preference for violent explanations. When something is broken, we assume it was struck. When something is out of place, we assume it was moved by force. When a planet spins in the wrong direction, we assume something hit it hard enough to turn it around. This instinct is not stupidity. It is pattern recognition, built from 10,000 years of experience in a world where things that are displaced generally got that way because something displaced them. A rock does not roll uphill on its own. A door does not swing open without a cause. A planet, the intuition insists, does not reverse its rotation without something enormous and catastrophic forcing it to. This instinct, when applied to Venus, led science down a road that was entirely reasonable, carefully constructed, mathematically explored, and ultimately insufficient. The collision hypothesis is not wrong. Exactly. It is incomplete in ways that took decades to fully appreciate. And the process of discovering its incompleteness reveals something important, not just about Venus, but about the nature of scientific explanation itself, about what it means to find an answer that fits, and then slowly realize that the fit is not quite right. To understand why impact was the first serious hypothesis, you need to understand what the early solar system actually looked like. We tend to imagine the solar system as it appears today, an orderly arrangement of planets moving in stable, predictable orbits around a steady sun, separated by vast and mostly empty distances. This is the solar system of textbooks and planetarium shows. It is accurate as a description of the present. It is profoundly misleading as a picture of the past. In the first several 100 million years of the solar system's existence, the space between the forming planets was not empty. It was filled with planetesimals, rocky and icy bodies ranging from hundreds of meters to thousands of kilometers across, hurtling through the inner solar system in chaotic crossing orbits, colliding with each other and with the growing planets at velocities and frequencies that strain imagination. This period, sometimes called the late heavy bombardment, was an era of almost incomprehensible violence. The surfaces of the Moon and Mercury, pockmarked with ancient craters that have been preserved across billions of years, are the closest thing we have to a visual record of what that time looked like. In that environment, massive impacts were not exceptional events. They were the mechanism of planetary construction. The planets were not formed and then struck. They were, in a very real sense, formed by being struck, assembled through accretion, shaped through collision, their final compositions and configurations determined by a process of sustained bombardment that lasted hundreds of millions of years. The evidence is everywhere. Mercury's extraordinarily high density, far higher than its size alone would predict, is almost certainly the result of a catastrophic impact that stripped away much of its rocky mantle, leaving the dense iron core disproportionately exposed. The Moon, as mentioned, exists because a body roughly the size of Mars collided with the proto-Earth at an oblique angle, ejecting enough material to form a natural satellite, and Uranus, which rolls along its orbital path with an axial tilt of 98 degrees, essentially spinning on its side, is the most dramatic exhibit in the case for impact as a planetary sculptor. Something enormous hit it. Something enormous changed it. The universe has been perfectly willing, throughout its history, to rearrange worlds through brute force. Given all of this, the idea that a large body struck Venus and reversed its rotation was not a wild guess. It was a reasonable scientific hypothesis, backed by extensive precedent and consistent with everything we knew about the early solar system. The mechanics of the hypothesis work, up to a point. Angular momentum, the quantity that describes how fast and in what direction something rotates, is conserved in a closed system, but it can be transferred. When a massive body strikes a planet, it transfers angular momentum from the impactor to the planet. Depending on the angle, speed, mass, and point of impact, this transfer can alter the planet's spin in dramatic ways. It can slow a rotation, it can tilt an axis, and in principle, it can reverse a direction entirely. For Venus, the scenario typically proposed involves an impactor of substantial size, somewhere between the mass of a large asteroid and a small planetary body, striking at a particular angle that maximized the retrograde torque transferred to the planet. The collision would not need to be perfectly head-on. In fact, an oblique impact, one that struck the planet from a particular direction at a particular angle, would be far more effective at altering the rotational state than a direct collision, which would primarily add energy to the system without cleanly reversing its spin. Computer modeling of such scenarios produces results that are, at first glance, encouraging. You can, with the right parameters, create models in which a large, oblique impact on a prograde rotating Venus results in a retrograde rotational state. The physics permits it. The early solar system had plenty of objects large enough to do it. The timing could be consistent with what we know about the bombardment history of the inner solar system. And yet, the axial tilt problem does not go away. This is the detail that refuses to be tidied into the impact narrative. The loose thread that, when you pull it, begins to unravel the entire explanation. Venus has an axial tilt of approximately 3 degrees. 3 degrees. For all practical purposes, it is perfectly upright, perfectly perpendicular to its orbital plane, sitting with a geometric precision that seems almost engineered rather than natural. And this matters enormously because the physics of angular momentum transfer does not allow you to selectively reverse a rotation while leaving the axis undisturbed. An impact large enough to reverse the spin of a planet with Venus's mass, more than 4.5 quintillion tons of rock, metal, and molten interior, would necessarily deliver enough energy and angular momentum to also significantly alter the planet's axial orientation. You cannot hit something that hard, at the angle required to flip its rotation, without also knocking it sideways to some meaningful degree. The models confirm this. When researchers run simulations of impact scenarios capable of reversing Venus's rotation, the resulting axial tilts are not 3 degrees. They are substantially larger. The collision that turns Venus backwards also, invariably, tilts it, and the Venus we observe is not tilted. This is a quiet but serious problem. There are ways to rescue the impact hypothesis from this objection, and scientists have explored them with considerable creativity. One possibility is that Venus was struck not once but multiple times, with subsequent impacts partially correcting the axial tilt that an initial retrograde-inducing collision would have introduced. Another possibility involves the subsequent action of tidal forces, the slow gravitational interaction between Venus, the Sun, and the dense atmosphere, gradually pulling the planet's axis back toward vertical over billions of years after an initial impact had reversed the rotation. Both of these scenarios are physically possible. Neither of them is simple. Both of them require a sequence of events so specific and so finely tuned that the probability of the whole chain occurring exactly as required begins to feel uncomfortably low. Science is not mathematics. Improbable events occur. The formation of the moon required an improbable collision. The existence of Earth's climate, stable enough over 4 billion years to allow the emergence of complex life, required an extraordinary sequence of improbable circumstances. Improbability is not impossibility. But when an explanation requires multiple, sequential improbabilities, each one essential to the outcome, the scientific instinct is to ask whether a simpler account exists. There is another problem with the impact hypothesis that rarely receives the attention it deserves, and it has nothing to do with axial tilt. It has to do with rotation rate. Venus rotates extraordinarily slowly, 243 Earth days per Venusian rotation. This is not merely slow in a relative sense. It is the slowest rotation of any planet in the solar system. Even Mercury, which was long thought to have a synchronous rotation locked to its orbital period, rotates faster than Venus relative to its own year. Now consider what an impact capable of reversing Venus's rotation would actually produce. The collision transfers angular momentum in the retrograde direction, but the quantity of angular momentum transferred depends on the size, speed, and angle of the impactor. For a body large enough to reverse the spin of a planet the size of Venus, the angular momentum transferred would be immense, not just enough to stop the original prograde rotation and set the planet spinning slowly backwards, but enough to set it spinning backwards at a significant rate. Yet Venus spins backwards almost imperceptibly slowly. If an impact reversed its rotation, what then removed most of the retrograde angular momentum, leaving the planet barely turning at all? Another impact? Tidal breaking acting over billions of years? The atmospheric tide working in reverse? Each answer requires another mechanism. Each mechanism requires another explanation. The collision hypothesis, the more closely you examine it, does not so much solve the problem of Venus's rotation as it relocates the problem into a longer chain of subsequent events that must each be explained in turn. This is not how the best scientific explanations work. The best explanations simplify. They reduce the number of moving parts. They take a complex phenomenon and reveal a single, elegant underlying cause that accounts for everything at once. The impact hypothesis for Venus's retrograde rotation does the opposite. It multiplies the required causes. None of this means the impact hypothesis is definitively wrong. There are planetary scientists who still consider it viable, who argue that the right combination of initial collision and subsequent tidal evolution can produce the Venus we observe today. The debate has not been formally closed. Science does not close debates through decree. It closes them slowly, provisionally, never quite completely, through the accumulation of evidence and the development of more powerful models. What has happened over the past 2 decades is that a different class of explanation has accumulated considerably more evidence and produced considerably more powerful models. An explanation that does not require a catastrophic collision at all. An explanation that requires only the patient, continuous operation of forces that have been acting on Venus since the moment it formed. And this explanation is, in some ways, more unsettling than the impact hypothesis. Because a collision is a one-time event, something that happened in the distant past to a young planet in a violent solar system, under conditions that no longer apply. It is historical. It is finished. It cannot happen again. But an explanation based on the slow grinding of atmospheric forces and tidal interactions operating over billions of years is something else entirely. It is a description of processes that are still occurring, processes that are not unique to Venus, processes that act on every planet with an atmosphere and a nearby star, processes that act on Earth. The shift away from the impact hypothesis and toward what might be called the tidal atmospheric hypothesis was not a sudden revolution. It was a gradual reorientation driven by better data, more sophisticated computational models, and a growing appreciation of just how much work planetary atmospheres can do over geological time. The key insight is this: the atmosphere of Venus is not just a layer of gas sitting passively on the planet's surface. It is a dynamic, massive structure, roughly 90 times the atmospheric mass of Earth, that interacts with the sun's gravity in ways that generate real, measurable torques on the planet itself. The sun pulls on the atmospheric bulge. The atmospheric bulge pulls on the planet. Over billions of years, this interaction has the potential to dramatically alter the planet's rotation without a single collision, without a single dramatic event, through nothing more than the patient application of physics. This is the hypothesis that, in 2021, Alexander Correa and his colleagues at the University of Aveiro developed into its most complete mathematical form, and the results of their modeling were striking. Without any impact at all, starting from a prograde rotating Venus with a thick atmosphere, their models produced a final rotational state consistent with what we observe today. The slow retrograde rotation, the near vertical axial tilt, the equilibrium between solid tidal friction pulling one way and atmospheric tidal torque pulling the other. No collision required. But this answer, compelling as it is, carries within it a question that the impact hypothesis never had to face. If Venus's thick atmosphere is what reversed its rotation, then the atmosphere must have been thick early in Venus's history, thick enough, dense enough, massive enough to exert the torques required over the timescales involved. And if that is true, then the question is not simply why Venus spins backwards. The question is why Venus developed an atmosphere so different from Earth's, so much earlier, so much thicker, so much more catastrophically hostile. Two planets, same origin, same mass, same neighborhood, same starting materials. One of them became the world you are standing on right now. The other became something that, by every measure, should not exist in the same solar system. The retrograde rotation of Venus is not the deepest mystery. It is the symptom, and the disease that caused it, the process that separated Venus from Earth, that turned a twin into a nightmare, is a story that reaches further back in time and further forward in consequence than anything a simple impact could explain. To understand why Venus spins backwards, you must first understand what Venus's atmosphere actually is, where it came from, what it did to the planet, and what it might, under different circumstances, do to another one. The atmosphere of Venus is not just the mechanism of its reversed rotation, it is the record of a catastrophe that has been written in retrograde motion and sulfuric acid clouds, sitting in plain sight in the evening sky, waiting to be read. When most people hear the word tide, they picture water. They picture the ocean pulling back from a beach in the early morning, exposing wet sand and stranded shells, and then returning hours later with quiet inevitability. They picture the moon hanging above the horizon and the invisible thread of gravity connecting it to the sea below, lifting billions of tons of water in a slow global pulse that has been beating since before any living thing existed to notice it. Tides, in the common imagination, are a coastal phenomenon, a maritime rhythm, something that fishermen and surfers track and that everyone else ignores. This understanding is not wrong. It is simply radically, almost embarrassingly incomplete. Because tides are not about water. They are not even about oceans. Tides are about gravity acting on any body that has mass and size, which is to say, gravity acting on everything. The solid rock beneath your feet is subject to tidal forces. The molten iron of Earth's outer core is subject to tidal forces. The crust of the moon flexes and compresses by measurable amounts as it moves through the varying gravitational field of Earth. Tides act on atmospheres. Tides act on stars. Tides, operating over sufficient timescales, can reshape the rotational states of entire planets. And on Venus, the tides of the sky may have done exactly that. To understand atmospheric tides, you need to understand what an atmosphere actually does when a star shines on it. This is not as simple as it sounds. When sunlight strikes the day side of a planet, it does not merely warm the surface. It interacts with the atmosphere in complex, layered ways, heating different gases at different altitudes, driving convective currents, creating pressure gradients that propagate outward through the atmospheric column like ripples through water. The result, on any planet with a thick enough atmosphere, is a phenomenon known as a thermal atmospheric tide. On Earth, this effect exists, but is subtle. Our atmosphere is thin enough, and our solid body massive enough, that the thermal tide creates only small, measurable fluctuations in surface pressure, fluctuations that meteorologists have been recording since the Yadi 19th century, a twice-daily pressure wave that moves around the planet following the sun. It is a curiosity more than a force. On Earth, it does not meaningfully alter the planet's rotation, not in any time frame that matters to us. On Venus, everything is different. On Venus, everything is amplified to a degree that transforms a curiosity into a mechanism of planetary scale consequence. Venus's atmosphere is, by any measure, extraordinary. The surface pressure on Venus is approximately 92 bar, 92 times the atmospheric pressure at sea level on Earth. The atmosphere is composed almost entirely of carbon dioxide, dense and heavy, and chemically stable, retaining heat with a ferocious efficiency that drives surface temperatures to 465 degrees Celsius, regardless of latitude, regardless of altitude, regardless of whether you are standing in perpetual daylight or perpetual night. The atmospheric mass of Venus is roughly 93 times the atmospheric mass of Earth. In absolute terms, you could take every molecule of air in Earth's atmosphere and multiply it by 93, and you would begin to approximate the weight of what sits above the Venusian surface. This is not merely a larger version of an Earth-like atmosphere. It is a fundamentally different kind of object. It is an atmospheric ocean, and like an ocean, it has dynamics, currents, waves, pressure systems that operate on scales and with energies that dwarf anything in Earth's meteorological experience. When the sun shines on this atmospheric ocean, it creates a thermal bulge, an enormous concentration of heated, expanded gas on the day side of the planet, lagging slightly behind the sun's apparent position as Venus rotates. This bulge is not stationary. It moves, or rather, the planet rotates beneath it, and the bulge lags, held back by the thermal timescale of the atmospheric heating. The result is that the atmospheric mass is never perfectly aligned with the sun. There is always an offset, always a slight asymmetry between the side of the planet facing the sun and the position of maximum atmospheric density and pressure. And that asymmetry is where the physics becomes extraordinary. The sun exerts a gravitational pull on everything it can reach, including Venus's atmosphere, a gravitational force acting on an asymmetrically distributed mass. An atmospheric bulge offset from perfect solar alignment produces a torque, a rotational force. The sun is, in effect, reaching across 108 million kilometers of space and pulling on the thick atmospheric tide of Venus, trying to drag that atmospheric bulge back into alignment. This pull acts on the atmosphere, and through the atmosphere, it acts on the planet beneath it. The direction of this torque depends on the details of the geometry, on whether the atmospheric bulge leads or lags the subsolar point, on the specific thermal response time of the atmosphere, on the rotation rate of the planet. The mathematics is not trivial, and getting it right required decades of increasingly sophisticated modeling. But the conceptual essence is this. The sun's gravity, acting on Venus's massive, offset atmospheric tide, generates a torque that can, over sufficiently long timescales, alter the planet's rotation, not by delivering a single impulsive force, the way a collision would, but by applying a continuous, gentle, unrelenting pressure, day after day, year after year, million year after million year, across billions of years of geological time. This is the atmospheric tidal torque, and it does not operate in isolation. Working against it, or in some configurations, working with it, is the solid tidal torque. The solid body of Venus, like the solid body of any planet, also experiences tidal deformation from the sun's gravity. The planet is not perfectly rigid. It flexes, very slightly, in response to the gravitational gradient across its diameter. The fact that the side of Venus facing the sun is gravitationally attracted more strongly than the side facing away. This differential gravitational force creates a slight elongation in the solid planet, a tidal bulge in the rock itself, analogous to the way Earth's oceans bulge toward the moon. This solid tidal bulge also lags slightly behind perfect solar alignment because the rock does not respond instantaneously to the gravitational forcing. It has internal friction, internal viscosity, internal resistance to deformation. And just as with the atmospheric bulge, the sun's gravity pulling on this misaligned solid bulge generates a torque, the solid tidal torque, for a planet rotating faster than its synchronous rate, which was almost certainly the case for early Venus, acts as a brake. It removes angular momentum from the rotation, slowing it down. This is the same mechanism that has been slowing Earth's rotation over geological time, very gradually lengthening our day at a rate of approximately 1.4 milliseconds per century. On Venus, closer to the Sun and subject to stronger solar tidal forces, this braking effect would have been more pronounced. So you have two torques acting on Venus: the solid tidal torque, braking the rotation, and the atmospheric tidal torque, which, depending on the rotational state of the planet and the properties of the atmosphere, can either add to the braking or oppose it. The question is, what is the equilibrium? Alexandre Correa, a planetary scientist at the University of Aveiro in Portugal, along with his longtime collaborator, Jacques Lascar, at the Paris Observatory, spent years developing the mathematical framework to answer exactly this question. Their work, published and refined across multiple papers over more than 2 decades, with a particularly comprehensive treatment appearing in Nature Astronomy in 2021, produced results that fundamentally change the way planetary scientists think about Venus's rotational history. The core finding was this: for a Venus-like planet with a sufficiently thick atmosphere, there exists a stable rotational equilibrium that is slow, that is retrograde, and that is consistent with a near-vertical axial tilt. The atmospheric tidal torque, acting in opposition to the solid tidal torque, does not simply slow the planet down and lock it into synchronous rotation the way the moon is locked to Earth. Instead, it finds a balance point, an equilibrium state, in which the solid tide's braking tendency and the atmospheric tide's driving tendency cancel each other out, leaving the planet spinning slowly in the retrograde direction. Venus, in this model, did not need to be hit. It did not need a catastrophic ancient collision to reverse its rotation. It needed only to have been born with the right atmosphere, and the physics would do the rest, patiently, invisibly, inevitably, over billions of years. The elegance of this explanation is striking. The Zawi 243-day retrograde rotation, the near-vertical axial tilt, the extreme slowness of the spin, all of it falls out naturally from the mathematics of competing tidal torques operating over geological time. No special impactor required. No finely tuned sequence of sequential collisions. Just physics. But the elegance of the explanation is inseparable from the enormity of what it requires us to accept. And what it requires us to accept is something that should feel, when it properly lands, considerably more than merely interesting. If the atmospheric tidal mechanism is correct, and the current consensus in planetary science leans substantially in its direction, then Venus's retrograde rotation is not the result of a unique, one-off event in its particular history. It is the result of a general physical process that acts on any planet with a thick enough atmosphere orbiting close enough to its star. Any planet. That phrase deserves its own moment of consideration. The solar tidal forces acting on Venus are strong because Venus is close to the Sun. But the atmospheric component of the mechanism depends primarily on the mass and thermal properties of the atmosphere, not just on the orbital distance. A planet further from its star, but with a dramatically thicker atmosphere, could in principle be subject to similar atmospheric tidal dynamics. The specific numbers would differ, the timescales would differ, but the underlying physics is not restricted to Venus. It is not even restricted to our solar system. And here, the question that seemed to be about one unusual planet in our solar neighborhood becomes something considerably larger. Because if atmospheric tides can reverse a planet's rotation, and if the final rotational state of a planet is partly determined by its atmospheric mass, then the rotation of a planet and the composition of its atmosphere are not independent variables. They are coupled. They evolve together. And the atmosphere of Venus, that extraordinary, massive, suffocating shell of carbon dioxide that drives the atmospheric tide, is not just the mechanism of the retrograde rotation, it is a symptom of something that happened to Venus's climate, something that should not have happened, given where Venus formed and what it formed from, something that distinguishes it in a way that has nothing to do with initial conditions and everything to do with subsequent evolution from the planet you are standing on. There is a concept in climate science known as a runaway greenhouse effect. The term is used somewhat loosely in popular science, but its precise meaning is specific and sobering. In a stable planetary climate, there is a feedback mechanism that prevents surface temperatures from spiraling out of control. As a planet warms, it radiates more energy back into space, and this increased radiation acts as a cooling force, counterbalancing the warming and pulling the temperature back toward equilibrium. This is why Earth's climate, over geological timescales, has been remarkably stable despite enormous variations in solar output, atmospheric composition, and surface geography. The feedback is self-correcting, but there is a threshold, a point beyond which the feedback breaks down. If surface temperatures rise enough to begin significantly increasing the amount of water vapor in the atmosphere, and water vapor is itself a powerful greenhouse gas, the warming can become self-reinforcing. More warming produces more water vapor. More water vapor produces more warming. The feedback flips from negative to positive, and the climate begins to accelerate away from habitability rather than being pulled back toward it. This is the runaway greenhouse effect, and once it begins, there is no known natural mechanism that reverses it. Venus, the models strongly suggest, crossed that threshold at some point in its past. The surface temperature rose, whether from increased solar luminosity, ASI, change in atmospheric composition, volcanic activity, or some combination of all three, past the point where the self-correcting feedback could operate. The oceans, if they existed, began to evaporate. The water vapor entered the atmosphere and amplified the warming. The temperature climbed further. More water evaporated until there was no liquid water left, and the atmosphere was full of it, and the solar radiation began breaking the water molecules apart, releasing hydrogen into space, leaving oxygen behind to combine with surface rocks, and stripping from Venus the one element that, on Earth, has been the central protagonist of 4 billion years of biological history. And what remained was a dense, massive, carbon dioxide-dominated atmosphere. The very atmosphere that drives the tidal torque, that reversed the rotation. Follow the chain. Venus forms, for a period, perhaps a very long period, it is, by the current evidence, something closer to Earth than to the hell it is today. It may have had liquid water, it may have had a clement surface temperature, it may have had, in the early chapters of its biography, conditions that we would recognize. Then something tips the balance. The climate shifts. The greenhouse effect runs away. The oceans vanish. The atmosphere thickens catastrophically, filling with carbon dioxide and sulfur compounds, and the chemical residue of a world cooking itself from the inside. The atmosphere becomes what it is today, 92 times the pressure of Earth's air, dense enough to crush, hot enough to melt lead, persistent enough to drive enormous tidal bulges across the face of the planet. And those tidal bulges, over billions of years, interact with the sun's gravity and the planet's own solid body tidal response, and they grind the rotation down. They push against the original prograde spin. They find an equilibrium, and Venus ends up spinning slowly backwards, upright, almost motionless against the background of the solar system. The retrograde rotation is not the beginning of Venus's story. It may be closer to the end of it, the final state of a planet that went through something catastrophic enough to remake its atmosphere from the ground up. And the atmosphere that remains, the one doing the tidal work, the one driving the slow backwards spin, is, in a very real sense, the monument to that catastrophe. The gravestone, written in atmospheric physics and retrograde motion. But here is the question that the atmospheric tidal hypothesis raises and does not answer. Here is the door that this explanation opens without providing a key. If Venus's thick atmosphere is a symptom of a climate catastrophe, if the runaway greenhouse effect is what gave Venus the atmospheric mass required for the tidal mechanism to work, then we need to understand that catastrophe. We need to understand what caused it. We need to understand whether it was inevitable given Venus's position, or whether it was contingent, the result of specific events that might not have occurred, that might have gone differently. Because Venus did not begin as the world it is now. It began as something else, something that the models are beginning, with uncomfortable clarity, to describe. And what the models describe should make anyone standing on a pale blue planet at a comfortable distance from the sun pause for longer than is entirely comfortable. The catastrophe that made Venus's atmosphere, and through that atmosphere reversed its rotation, may have had a beginning that looked nothing like a catastrophe at all. There is a particular kind of unease that comes not from encountering something alien, but from encountering something familiar that has become unrecognizable. A face you once knew, altered beyond easy identification. A place you grew up in, transformed so completely that the street plan is the only thing left of what it was. The discomfort is not the strangeness itself. It is the knowledge of what the strangeness replaced. It is the gap between what was and what is, and the inability to fully account for how the distance between the two was crossed. Venus produces exactly this kind of unease, not because it is utterly unlike Earth, but because, by every measurement that should matter, it began as something extraordinarily like Earth and ended as something that represents, with almost deliberate comprehensiveness, the precise opposite of every condition that makes life on our planet possible. To understand Venus fully, to understand what its retrograde rotation is actually a symptom of, you have to begin at the beginning. You have to go back to the moment of formation and ask the question that planetary science has been circling for decades with growing discomfort. How do two essentially identical planets end up so catastrophically different? The numbers, stated plainly, are almost philosophically provocative. Venus has a mass of approximately 4.87 times 10 to the power of 24 kilograms. Earth has a mass of approximately 5.97 times 10 to the power of 24 kilograms. Venus is roughly 82% of Earth's mass, close enough that in any other context, you would call them the same. Their diameters differ by less than 600 kilometers. Their bulk compositions, the ratios of rock to metal, the proportions of silicon and iron and magnesium, are, as best as we can determine from remote measurements and the limited data returned by surface landers, broadly similar. They formed from the same disk of protoplanetary material during the same period of solar system history, through the same process of accretion and differentiation. They are, in the language of planetary science, sister planets, twins, in the loose but meaningful sense that their initial conditions were more similar to each other than either was to any other body in the solar system. Venus orbits the Sun at an average distance of 108 million kilometers. Earth orbits at 150 million kilometers. The difference, 42 million kilometers, sounds substantial in everyday terms. In the context of a solar system that extends billions of kilometers to its outer edges, it is a narrow margin. Venus sits just inside the inner boundary of what astronomers call the habitable zone, the orbital band where liquid water can exist stably on a planetary surface. Earth sits comfortably within it. The difference between a world that hosts life and a world that destroys it, in spatial terms, is roughly the distance between London and the Moon, multiplied by 110. On the scale of the cosmos, this is nothing. On the scale of lived experience, it is everything. For most of the 20th century, scientists assumed that Venus had always been hot, that its proximity to the Sun had always made it inhospitable, that the thick atmosphere and the extreme surface temperatures were original features of the planet, baked in from the beginning by the simple mathematics of orbital distance and solar flux. This assumption was comfortable. It preserved a clean, simple distinction between Earth and Venus. One planet was close enough to the Sun to be hostile. The other was at the right distance to be habitable. The difference was geometric, fixed, and ancient. The assumption began to collapse in the 1990s when improved climate models and better understanding of planetary atmospheric evolution started producing results that were increasingly difficult to reconcile with the idea of a Venus that had always been as it is today. The models suggested that the young Sun, smaller, cooler, and roughly 30% less luminous than it is now, would not have been able to drive the kind of extreme greenhouse warming observed on modern Venus if Venus had begun with an Earth-like atmosphere. Something had changed. The current state of Venus was not the original state. The collapse of the assumption accelerated in 2016 and again in 2019, when Michael Way at NASA's Goddard Institute for Space Studies and his collaborators published a series of increasingly detailed climate simulations examining what Venus might have looked like in its early history. The results were, depending on your perspective, either fascinating or deeply unsettling. The models suggested that Venus, for much of its early and middle history, was not a hell. It was, by every criterion the models could evaluate, potentially habitable. What Way and his colleagues found was this: if Venus formed with a surface water inventory comparable to Earth's, an assumption consistent with its formation from similar protoplanetary material, and if the young Sun's lower luminosity is properly accounted for, then Venus could have maintained stable liquid oceans for an extended period. Not briefly, not marginally, for what the models estimated at up to 3 billion years. 3 billion years of liquid, water, 3 billion years of moderate surface temperatures, 3 billion years during which on Earth, life went from single-celled organisms to complex multicellular forms. 3 billion years of what we might, without too much poetic license, call a livable world. The models placed Venus's early surface temperatures in a range broadly similar to Earth's current average, perhaps slightly warmer, but within the bounds of what we consider comfortable. The planet had a day-night cycle, even if its rotation was slower than Earth's. Atmospheric circulation would have distributed heat reasonably effectively. The surface would have had geology, mountains, lowlands, perhaps continental-scale features shaped by tectonic or volcanic processes. There is no certainty here. The models are models. They are built on assumptions that cannot all be verified from the present state of a planet that has erased most of its own surface record through what appears to have been a global volcanic resurfacing event roughly 500 million years ago. The direct evidence for an ancient Venusian ocean, the kind of geological record that, on Earth, extends back nearly 4 billion years, does not exist in accessible form, if it exists at all. But the models are not fringe science. They are the product of serious, peer-reviewed work, using the same computational frameworks that underpin our understanding of Earth's own climate history, and they converge on a picture that is, if not certain, at least scientifically credible. Venus may have been habitable for longer than it has been a hell. If that is true, if Venus genuinely spent billions of years as something resembling a clement, water-bearing world, then the question that follows is the most important one in this entire story. What ended it? The answer is not fully known. This is not false modesty or scientific hedging. It is the honest state of the field. What we have is a set of plausible mechanisms, each supported by some evidence, none of them proven in isolation, and the question of how they combined, of what the actual sequence of events was, and what triggered the first step in the catastrophe, remains genuinely open. But the mechanisms themselves are worth examining carefully, because each one, in isolation, is not exotic. Each one is a process that operates in our own world today. The horror of what happened to Venus is not that it was destroyed by something alien and incomprehensible. The horror is that it was destroyed by things that are entirely familiar, operating in a configuration that tipped an equilibrium that had held for billions of years. The first mechanism is solar evolution. The sun is not constant. Over its lifetime, it gradually increases in luminosity, burning hotter and brighter as the hydrogen fuel in its core is consumed and helium ash accumulates. Over the 4.5 billion years since the solar system formed, the sun's luminosity has increased by approximately 30%. The young sun that illuminated the early solar system was substantially dimmer than the sun that rises over your horizon each morning. This steady increase in solar output would have slowly raised the energy input received by Venus's surface over geological time. A planet that was in thermal equilibrium, comfortably balancing energy, received against energy radiated, at one solar luminosity, would gradually warm as that luminosity increased. For a planet sitting right at the inner edge of the habitable zone, this gradual warming would, at some point, begin to push the surface temperature toward a critical threshold. The threshold is this: the point at which the warming is sufficient to trigger significant evaporation of surface water into the atmosphere. Water vapor is a far more effective greenhouse gas then carbon dioxide, weight for weight. As surface water evaporates, the atmospheric concentration of water vapor rises, which traps more heat, which causes more evaporation, which increases the water vapor concentration further. This is the positive feedback loop at the heart of the runaway greenhouse effect. Once it begins in earnest, it does not stop. The sun's gradual brightening over billions of years could, for a Venus-like world sitting at the inner edge of the habitable zone, have been the slow trigger that eventually crossed the threshold. But solar evolution alone may not be sufficient to explain the timing. The models suggest that other factors were probably involved, compounding the solar forcing and accelerating the transition. The second mechanism is volcanism, and Venus, from everything we can determine, has been extraordinarily volcanically active. The Magellan spacecraft, which mapped Venus's surface using radar between 1990 and 1994, revealed a planet with a geological character unlike anything in the inner solar system. The surface is dominated by volcanic features on a scale that dwarfs Earth's volcanic activity. Vast plains of solidified lava flows, enormous shield volcanoes, and strange formations called coronae and tesserae that suggest a geological history of intense, sustained volcanic outgassing. More recent observations, including data from the European Space Agency's Venus Express mission and analysis published as recently as 2023, have found evidence suggesting that Venus may still be volcanically active today. The surface, in some regions, appears to have been modified in geologically recent times. Recent here, meaning within the last few 100,000 to million years. For the question of what ended Venus's habitability, volcanism is significant for a specific reason. Volcanic activity releases carbon dioxide, enormous quantities of it, over geological time. On Earth, this release is counterbalanced by the carbon silicate cycle, a geological feedback mechanism in which carbon dioxide is drawn down from the atmosphere by the weathering of silicate rocks, incorporated into carbonate minerals, and eventually returned to the mantle through plate tectonics. This cycle acts as a long-term thermostat for Earth's climate, preventing the atmospheric carbon dioxide concentration from spiraling out of control. Venus appears to have lost this thermostat, whether because its tectonic regime differs fundamentally from Earth's. There is no clear evidence of plate tectonics on Venus as we understand it, or because the loss of surface water eliminated the liquid medium in which silicate weathering operates. The carbon silicate cycle appears to have broken down on Venus. Without it, volcanic carbon dioxide accumulated in the atmosphere rather than being drawn back down. The greenhouse effect intensified. The surface warmed further. The remaining surface water evaporated. The feedback ran away. The specific trigger may have been a period of unusually intense volcanism, a large igneous province event, comparable to the volcanic episodes that have, on Earth, been associated with mass extinction events. Venus may have experienced such an episode with a climate system already weakened by billions of years of gradually increasing solar flux, sitting too close to the inner edge of the habitable zone to absorb the additional forcing without tipping into the runaway. The third mechanism concerns something whose absence on Venus is, in retrospect, glaring. Venus has no magnetic field of any significance. Earth's magnetic field is generated by convective motion in the liquid outer iron core, a dynamo process that requires both a molten metallic core and sufficient energy to drive the convection. The field that results is not merely a navigational convenience, it is a planetary shield, deflecting the charged particles of the solar wind away from the upper atmosphere and preventing them from gradually stripping away the lighter atmospheric gases. Without a magnetic field, a planet's atmosphere is exposed directly to the solar wind. The process of atmospheric stripping, called sputtering, is slow but relentless. Over billions of years, it can remove substantial quantities of lighter gases from an unprotected atmosphere. Crucially, it preferentially removes hydrogen, the lightest element, the element that, combined with oxygen, makes water. If Venus lost its magnetic field early in its history, whether because its core cooled and solidified too quickly, or because its internal dynamics evolved differently from Earth's, then the solar wind would have been stripping hydrogen from its upper atmosphere for billions of years. This hydrogen loss is directly equivalent to water loss. Each hydrogen atom lost to space represents a fraction of a water molecule that can never be reconstituted. Over geological time, this slow hemorrhage of hydrogen could have meaningfully depleted Venus's water inventory, gradually drying out the surface and concentrating the remaining carbon dioxide in an atmosphere increasingly unable to sustain. Liquid water. We cannot be certain when or why Venus lost its magnetic field. We do not know whether it ever had a field as strong as Earth's, or whether it was always magnetically weak. These are questions that no current spacecraft mission can answer, because the evidence is buried beneath a surface that has been volcanically resurfaced and atmospherically processed to a degree that has obliterated most of the accessible record. What we have, then, is not a single cause. We have a convergence, a slow brightening sun pushing Venus's surface temperatures gradually upward over billions of years, a volcanic regime that pumped carbon dioxide into the atmosphere without adequate geological mechanisms to draw it back down, a missing or weakened magnetic field that allowed the solar wind to steadily drain the planet's water. Three separate processes, each insufficient on its own to explain the catastrophe, but together forming a compounding sequence of feedbacks that, at some point, crossed a threshold from which there was no return. The climate destabilized. The oceans evaporated. The water vapor amplified the warming. The hydrogen escaped to space. The oxygen combined with surface rocks. The carbon dioxide accumulated. The temperature climbed to what it is today and has remained there, stable in its hellishness, for what may be hundreds of millions of years. And the atmosphere, thick, massive, crushing, the product of this entire catastrophic history, became the engine of the atmospheric tide, the mechanism that, over subsequent hundreds of millions of years, ground Venus's rotation down and reversed it. The retrograde spin is, in the deepest sense, the fingerprint of the catastrophe. It is what a dead climate leaves behind when it has had long enough to reach its final equilibrium. There is a version of this story that stops here, that treats Venus as a cautionary tale about orbital proximity, a planet that was always slightly too close to the sun, always slightly too exposed to the forces that would eventually unmake it, doomed by geometry from the beginning. But that version is not what the models show. That version requires Venus to have always been inhospitable, which the climate simulations increasingly contradict. The version the models show is stranger and considerably less comfortable. The models show a planet that was fine, a planet that was, by any reasonable definition, alive with the possibility of complexity, covered in liquid water, warmed by a young sun to temperatures that any terrestrial organism would recognize as tolerable, stable for billions of years in that state. And then the version the models show has that planet ending, not gradually, not imperceptibly, but On geological timescales, suddenly, a threshold crossed, a feedback triggered, a world that went from habitable to lethal within a period that, relative to its long prior history, amounts to almost nothing. One world became two outcomes. One outcome you are reading this from. The other is turning slowly in the night sky, a brilliant point of light that has been regarded for millennia as a symbol of beauty, spinning backwards above a surface that has not seen liquid water in what may be hundreds of millions of years. The gap between those two outcomes is not as wide as it should be. The processes that destroyed Venus are not unique to Venus. They are processes we understand, processes we can model, processes that, under different conditions, act on different worlds, worlds like this one. And that is not a rhetorical observation, it is a scientific one. Because the question of what separates a living world from a dead one, what sits at the boundary between Earth's outcome and Venus's outcome, is not a question that has been fully answered. It is a question that is, right now, one of the most actively studied problems in planetary science. The twin that went wrong is not just a story about Venus, it is a reference point, a data point in a sample size of two, the only two planets we know of that began in similar enough conditions that comparing their outcomes tells us something real about the fragility of the conditions that allow worlds like ours to persist. And what the comparison tells us leads, in the next part of this story, to a territory that is considerably less abstract than atmospheric chemistry and orbital mechanics. It leads to the question of life, whether it existed on Venus, whether its absence or its presence contributed to the catastrophe, and what the answer to that question, whichever way it falls, means for the only living world we are absolutely certain still exists. There is a question that planetary scientists have been trained, by professional habit and institutional caution, to approach with extreme care. It is not a technically difficult question. It does not require advanced mathematics or specialized instrumentation to state. A child could ask it without any understanding of orbital mechanics or atmospheric chemistry. But the implications of the question, the weight of what its answer would mean in either direction, are significant enough that scientists tend to lower their voices slightly when they approach it, to qualify their language with unusual precision, to surround the core of the idea with careful hedges and measured caveats. The question is this: was there ever life on Venus? For most of the 20th century, this question was not taken seriously in mainstream science. The surface of Venus, once revealed by spacecraft, was obviously and catastrophically hostile to any biology we understand. The temperature, the pressure, the chemistry, nothing about the modern Venusian environment is compatible with life as we know it. The question seemed answered before it was properly asked. A world that melts, lead on its surface, and rains sulfuric acid from its upper cloud layers is not a world you spend serious scientific effort searching for biosignatures. But that calculus has changed, and the change is not the result of wishful thinking or the loosening of scientific standards. It is the result of the same climate models that revealed Venus's potentially habitable past, and of a separate, stranger discovery made in 2020 that sent the question of Venusian life from the margins of planetary science into the center of one of the most significant debates in modern astronomy. To understand either development, you need to sit with what the models actually imply, not as an abstract possibility, but as a concrete historical scenario. If Venus was habitable for up to 3 billion years, If liquid oceans existed, if surface temperatures were moderate, if the atmospheric chemistry was broadly comparable to early Earth, then Venus was not merely a place where life could have existed in principle. It was a place where, if our understanding of biology's relationship to planetary environments is correct, life had every opportunity to emerge. Life on Earth appeared astonishingly quickly by geological standards. The oldest confirmed microbial fossils date to approximately 3.5 billion years ago. Chemical signatures, consistent with biological activity, may extend back further still, to 3.7, possibly even 4.1 billion years ago. Within a few hundred million years of Earth's formation and the end of the late, heavy bombardment, life did not wait for Earth to become comfortable and then cautiously experiment with biochemistry. It appeared at the earliest possible opportunity, in conditions that were, by our current standards, quite harsh. The implication drawn from Earth's early biological history is that life, given liquid water, the right chemical building blocks, and sufficient time, tends to emerge. Not inevitably, we have only one confirmed example, and a sample size of one supports no statistical generalizations. But the speed of life's appearance on Earth suggests that the origin of life is not an extraordinarily improbable event that required billions of years of chemical searching. It appears to be something that happens relatively readily when the conditions are met. Venus met those conditions. For 3 billion years, the models suggest, Venus met those conditions. If life operates on Venus anything like the way it operated on early Earth, then 3 billion years is more than enough time for it not only to emerge, but to develop substantial complexity. On Earth, 3 billion years was enough time to go from the first uncertain chemistry of self-replicating molecules to the Cambrian explosion of multicellular animal life. 3 billion years of Venusian biology, if it existed, could have produced something we would recognize, something with structures and metabolisms and ecological relationships before the catastrophe ended it all. This is not a claim that life existed on Venus. It is a statement about what the timeline permits. And what the timeline permits should be taken seriously, because it transforms Venus from a planet that happens to have a backwards rotation into something considerably more confronting. It transforms Venus into a world that may have lived and died. The 2020 discovery that brought the question of Venusian life into sharp scientific focus was, on the surface, a fairly specific chemical claim. A team led by Jane Greaves at Cardiff University announced the detection of phosphine in Venus's upper atmosphere. Phosphine is a molecule composed of one phosphorus atom and 3 hydrogen atoms. On Earth, it is produced in 2 primary ways: through industrial chemistry and through biological metabolism. Certain anaerobic microorganisms, bacteria that thrive in oxygen-free environments, produce phosphine as a byproduct of their biochemical processes. It is found in swamps, in the intestines of animals, in organic sediments. Its presence, in an astronomical context, is considered a potential biosignature, a chemical signature whose production by purely geological or atmospheric processes is difficult to explain without invoking biology. The announcement was immediately controversial. The initial paper claimed a detection of phosphine at a concentration of approximately 20 parts per billion in Venus's cloud layers, at altitudes between 50 and 60 kilometers above the surface. Subsequent reanalyses of the data, both by the original team and by independent researchers, produced lower and more uncertain estimates. The quality of the original spectroscopic data was questioned. The statistical significance of the detection was debated with unusual intensity across multiple published papers. As of the current state of the literature, the phosphine detection remains contested. It has not been confirmed by independent observations to a degree that would satisfy most planetary scientists. It has not been definitively refuted either. It exists in the frustrating scientific space between a claimed discovery and a confirmed one, a space that can only be resolved by better data from better instruments, preferably from a spacecraft in Venus's atmosphere. But the phosphine controversy, regardless of how it is ultimately resolved, did something important and lasting. It forced the scientific community to take seriously the question of what is actually happening chemically in Venus's upper cloud layers, and to confront how poorly that environment is currently understood. The cloud layers of Venus, at altitudes between roughly 48 and 60 kilometers above the surface, are one of the strangest environments in the solar system. At those altitudes, something remarkable happens. The temperature drops to a range between 0 and 90 degrees Celsius, warm by human standards, but not lethally so. The pressure at the upper cloud boundary is approximately 1 atmosphere, essentially the same as Earth's sea level pressure. These are, by the standards of Venus's surface, almost benign conditions. Certainly they are conditions in which Earth-based biochemistry could, in principle, operate. The complication, of course, is the sulfuric acid. The clouds of Venus are composed primarily of concentrated sulfuric acid droplets, between 75 and 96% sulfuric acid by concentration, suspended in the atmosphere as a permanent planet-wide overcast. Sulfuric acid at those concentrations is extraordinarily hostile to most biological chemistry we understand. It destroys organic molecules. It denatures proteins. It is not, by any straightforward analysis, a hospitable medium for life. And yet, there are organisms on Earth, extremophiles, microbes that thrive in conditions that were once considered categorically incompatible with biology, that have adapted to environments of remarkable chemical hostility. Acidithiobacillus thiooxidans, a bacterium found in highly acidic mining drainage and volcanic hot springs, can survive in solutions approaching pH 0, pure acid by any practical definition. Other extremophiles have been found in conditions of extreme heat, extreme cold, extreme radiation, extreme salinity, and combinations thereof that would be lethal to any complex organism. Life, as Earth has repeatedly demonstrated, is more persistent, more inventive, and more chemically flexible than intuition suggests. The sulfuric acid clouds of Venus are extreme, but extremophile biology has shown that extreme is not the same as impossible. Carl Sagan and Harold Morowitz speculated as early as 1967, long before the phosphine controversy, long before the habitability models, that the Venusian cloud layers might be a plausible environment for aerial microbial life. Organisms small enough to remain suspended in the cloud droplets, metabolically adapted to the acid chemistry, cycling through the atmosphere as the convective dynamics of Venus's weather system carried them up and down through the cloud layers. The speculation was not taken seriously at the time. The atmospheric data was insufficient. The biological imagination of the era was constrained by an earthbound conception of what life required. The speculation has not gone away. In the wake of the phosphine controversy, it has, if anything, become more formally examined. Sarah Seeger at MIT and her collaborators have published detailed biological and chemical models of what a Venusian aerial microbial ecosystem might look like, how organisms might protect themselves from the acid, how they might metabolize the available chemical gradients in the cloud layers, how they might reproduce and disperse in a planetary atmosphere rather than on a planetary surface. These are not claims that life exists in Venus's clouds today. They are explorations of whether it is possible, and the answer the models return consistently is that it cannot be ruled out on physical or chemical grounds alone. Here is where the story of Venus becomes, in the deepest sense, a mirror. Consider the two scenarios. In the first, Venus was never inhabited. Life never emerged, despite 3 billion years of habitable conditions. The climate catastrophe destroyed an uninhabited world, leaving behind nothing biological, only geology and chemistry, and the slow reversal of a planetary rotation. In this scenario, Venus is a cautionary tale about climate instability, about the fragility of habitability, about what can happen to a world at the inner edge of a habitable zone when the wrong feedbacks are triggered. In the second scenario, Venus was inhabited. Life emerged, as it did on Earth, in the early period when conditions were favorable. It evolved over billions of years, developing complexity, colonizing whatever environments were available, doing what life on Earth has always done, finding ways to persist. And then the climate catastrophe came and ended it. Not immediately, not all at once, but over the geological blink of an eye that separates a habitable world from a dead one, perhaps over 1,000,000 years, perhaps over 10 million. The conditions that had sustained Venusian life for billions of years were swept away by the runaway greenhouse effect, the evaporation of the oceans, the loss of water to space, and whatever existed on Venus was extinguished. In this second scenario, Venus is not merely a cautionary tale. It is the closest thing to a confirmed extinction of an entire biosphere that we have ever encountered, not the extinction of a species, not the extinction of an ecosystem, the extinction of all life on an entire planet. Both scenarios are consistent with current evidence. We cannot distinguish between them with the data we have, and the inability to distinguish between them is itself a fact worth sitting with carefully, because the implications of the two scenarios for how we understand our own situation are radically different. If Venus was uninhabited, then the question of what separates Earth's outcome from Venus's is purely a physical and chemical one. Orbital distance, magnetic field strength, volcanic outgassing rates, tectonic regime, the presence or absence of specific feedback mechanisms in the climate system. These are variables that can, in principle, be understood and quantified. They speak to the fragility of planetary habitability in terms of physics and chemistry, which is sobering but tractable. We can, at least in principle, understand the rules of the game. If Venus was inhabited, the question deepens considerably, because one of the most important stabilizing mechanisms in Earth's climate system is biology itself. Life on Earth has not merely existed within Earth's climate. It has shaped it, stabilized it, and in several critical episodes, been responsible for the specific chemical composition of the atmosphere that keeps the greenhouse effect within habitable bounds. The Great Oxidation Event, approximately 2.4 billion years ago, fundamentally transformed Earth's atmosphere through the metabolic activity of photosynthesizing cyanobacteria, the biological pump, the movement of carbon from the atmosphere into the deep ocean through the death and sinking of marine organisms, is one of the primary mechanisms by which atmospheric carbon dioxide is regulated over geological time. Forests and soils are not merely habitats, they are massive, distributed carbon management systems that interact with the climate in ways that stabilize it against perturbations. If Venus once had life, then the question is whether Venusian life was performing analogous stabilizing functions, whether the biology, whatever form it took, was part of the climate system's self-correcting machinery, and if so, whether the disruption of that biology, perhaps by early volcanic activity, perhaps by the initial stages of atmospheric change, perhaps by something we have not yet imagined, contributed to the cascade that ultimately destroyed the climate entirely. This is a disturbing possibility. It suggests that the catastrophe that killed Venus may not have been purely physical. It may have had a biological component. The loss of life may have undermined the very feedback mechanisms that were keeping the climate stable, which accelerated the destabilization, which caused more life to die, which further weakened the feedbacks, in a spiral that ended not in the gradual geological change we might expect, but in the rapid, irreversible catastrophe the models describe, life destroying the conditions for life by dying. In 2021, NASA selected 2 new missions to Venus, Da Vinci and Veritas, as part of its Discovery program. The European Space Agency has its own Venus mission, Envision, scheduled for the early 2030s. Japan's Akatsuki orbiter continues to monitor Venus's atmosphere. Multiple private proposals for Venus atmospheric probes and surface landers are in various stages of development. After decades of relative neglect, Venus has become, suddenly and urgently, one of the most scientifically prioritized destinations in the solar system. The reasons are not unrelated to what this chapter has described. The scientific community has arrived, through the convergence of climate modeling, atmospheric chemistry, and the phosphine controversy, at a recognition that Venus contains answers to questions that are not merely about Venus, questions about the boundaries of habitability, questions about the relationship between life and climate stability, questions about what a world looks like when it crosses the threshold from one to the other, and whether there are warning signs that can be read in the geological and chemical record. If that record can be accessed, the missions are not being designed to look for life on modern Venus, though the possibility of aerial microbial biology in the cloud layers will be investigated by instruments designed to characterize atmospheric chemistry. They are being designed to read the history, to access whatever record remains of Venus's past, before the volcanic resurfacing and the atmospheric chemistry erased it, to determine, as precisely as current technology allows, when the habitability ended, how quickly it ended, and what the final conditions of the transition looked like. Because that transition, that moment when a world crosses from the side of life to the side of death, is the most important boundary in planetary science. And Venus is the only world in the solar system, other than Earth, that we have strong reason to believe was once on the living side of it. Look up at Venus on a clear night, and you are looking at a world that, by the current best models of planetary science, may have spent 3 billion years as something your biology would have recognized. A world with oceans, with weather, with a carbon cycle and a water cycle, and possibly, by the extension of everything we understand about life's relationship to favorable environments, with organisms of some kind going about the ancient, patient business of existing. And then look at it a second time and understand that what you are seeing now is what remains after the threshold was crossed. The brilliant, unwavering point of light in the evening sky is the afterglow of a catastrophe that the universe did not find exceptional, that the laws of physics permitted, and the specific configuration of Venus's orbit and atmosphere and geological history ultimately could not prevent. The mirror in the dark is not merely a poetic image, it is a scientific instrument. Venus, properly understood, is the closest thing to a controlled experiment in planetary habitability that the solar system provides. Same star, same general region, similar mass, similar composition, different outcome. And the variable, the thing that differs between the two outcomes, is not yet fully understood. That is the finding that should stay with you. Not that Venus is alien and hostile. Not that it is a dramatic example of what other planets can be like, but that the variable separating Earth's outcome from Venus's outcome, after 50 years of increasingly sophisticated planetary science, has not been fully and conclusively identified. We know the mechanisms involved. We do not know the precise configuration that triggered them. We do not know whether the trigger was inevitable, given Venus's position in the solar system, or whether it was contingent, the result of specific events that, under slightly different circumstances, might not have occurred. We do not know, with the certainty the question deserves, how similar the circumstances that produced Venus's outcome are to the circumstances currently present on Earth. And that uncertainty, held carefully, scientifically, without hysteria, but also without comfortable dismissal, is what the retrograde rotation of Venus is ultimately pointing at. Not just backwards, against the direction of the solar system's rotation, but inward, toward the question of what makes a world persist and what makes it end. The question behind the question has been building across every chapter of this story. It has been present in the atmospheric tides and the ancient impacts and the runaway greenhouse and the lost oceans. It has been accumulating, layer by layer, beneath the surface of what seemed, at the outset, like a simple astronomical curiosity. And in the final chapter, it arrives, not as an answer, but as the full, unobscured shape of what we are actually asking, which is not why Venus spins backwards. There is a particular kind of silence that follows the moment you realize a question is larger than you thought. Not the silence of confusion, not the silence of having nothing to say, but the silence that comes when understanding expands faster than language can follow, when the mind has moved to a new place and has not yet found the words that belong there. It is the silence of standing at the edge of something vast, looking out at it, and recognizing that what you are looking at does not have a comfortable boundary. This story began with a single planetary anomaly, a world spinning in the wrong direction, a number 243 Earth days per rotation, retrograde, that contradicted the inherited angular momentum of an entire solar system. It seemed, at the outset, like the kind of question that science eventually closes. Something happened to Venus. We will determine what it was. We will file the explanation. We will move on. It has not worked out that way. What began as a question about a planet's rotational direction has, across the preceding chapters, expanded through atmospheric physics and ancient impacts and planetary climate history and the possibility of extinct biospheres, until it has arrived here, at the edge of a question that is not about Venus at all, or not only about Venus, but about the stability of conditions that allow anything to persist. This final chapter does not close the mystery. It cannot. The honest and only accurate thing it can do is reveal the full shape of what we have been looking at all along. And the shape, when you step back far enough to see it whole, is considerably larger and stranger than a retrograde spinning planet deserves to be. Begin with what we know. We know that Venus and Earth formed from the same protoplanetary disk, at roughly the same time, from roughly the same materials, at orbital distances close enough that the difference in solar flux they received in the early solar system was measurable, but not dramatic. We know that Venus is, by mass and radius and bulk composition, the closest thing to Earth's twin that the solar system contains. We know that the current state of Venus, 465 degrees at the surface, 92 atmospheres of pressure, sulfuric acid clouds, no liquid water, no detectable biosignatures, is not, according to the best current climate models, its original state. We know, or have strong modeling reason to believe, that Venus was once habitable, that liquid water existed on its surface, that the conditions for the emergence of life, if life operates by the same general chemistry on Venus as it does on Earth, were present for a geologically substantial period. We know that something ended this, that a combination of increasing solar luminosity, volcanic carbon dioxide outgassing, the possible loss of a protective magnetic field, and the inherent instability of a world sitting at the inner edge of the habitable zone converged to trigger a climate transition that was, once initiated, irreversible. That the atmosphere thickened, that the oceans evaporated, that the water was lost to space, that what remained was a dense, massive, superheated shell of carbon dioxide that became the engine of the atmospheric tidal torque, that, over hundreds of millions of subsequent years, reversed the planet's rotation. We know that the retrograde spin of Venus is, in the deepest sense, the physical record of that catastrophe, the final rotational signature of a climate that destroyed itself. And we know, and this is the knowledge that sits most uncomfortably in the stomach of anyone who has followed this story carefully, that we do not fully understand why Earth did not follow the same path. This is not a rhetorical provocation. It is a scientific statement. The Earth is not obviously, structurally different from Venus in the ways that would make its different outcome inevitable. It is further from the Sun, yes, but not dramatically so. It has a strong magnetic field generated by its convecting liquid iron core. But why Earth's core has maintained this dynamo, while Venus's apparently has not, is a question that remains poorly understood. Earth has plate tectonics, which drives the carbon silicate cycle that regulates long-term atmospheric carbon dioxide concentrations. But why Earth developed active plate tectonics, while Venus did not, despite the two planets having similar compositions and thermal histories, is one of the outstanding unsolved problems in comparative planetology. Each of the differences between Earth and Venus that seems to explain their divergent outcomes turns out, when you press it, to require its own explanation. The answers do not terminate in the solid bedrock of understood physics. They retreat, question by question, into a region where the models are less certain, the data more sparse, and the confidence intervals wider than the conclusions drawn from them ought to comfortably permit. James Casting at Penn State University, one of the founders of the modern scientific study of planetary habitability, has spent decades working on the boundaries of the habitable zone, the mathematical framework that describes which orbital distances around which types of stars can sustain liquid water on a planetary surface, the inner edge of the habitable zone, the boundary inside which a planet risks the runaway greenhouse effect that destroyed Venus, is not a sharp line. It is a zone of uncertainty, a region where the outcome depends on factors beyond orbital distance alone: atmospheric composition, rotation rate, albedo, cloud cover, the presence or absence of biology. Earth, in Casting's models, sits comfortably within the habitable zone. But comfortably is a relative term, and the width of the comfort zone, the margin between Earth's current position and the inner edge where Venus's fate becomes possible, has been revised and debated by successive generations of climate models. And the answer is consistently less generous than anyone would prefer. Some models suggest that a planet with Earth's current atmospheric composition, placed at Venus's orbital distance, would rapidly enter a runaway greenhouse state. Others suggest that a Venus-like planet, given Earth's rotation rate and magnetic field and tectonic regime, might have remained habitable. The variables interact in complex, nonlinear ways that make clean conclusions difficult. What the modeling community has converged on over the past 20 years is something like this. The difference between Earth's outcome and Venus's outcome is real, but it is not large. It is the product of a specific configuration of variables that happened, in Earth's case, to remain on the right side of several critical thresholds. Had any one of a number of those variables been slightly different, had Earth formed slightly closer to the Sun, had its tectonic regime evolved differently, had its magnetic field weakened at an earlier stage, the path toward Venus's outcome would have been open. The margin is real. The margin is also uncomfortably narrow. This brings the story to a place that requires careful navigation. It would be easy, and it would be wrong, to read the preceding paragraphs as a claim that Earth is headed for Venus's fate. That is not what the science says. Earth's climate system is not on the verge of a runaway greenhouse transition. The timescales involved in the natural processes that gradually increase solar luminosity, the same process that eventually contributed to Venus's fate, operate over hundreds of millions to billions of years. The specific trigger conditions for a runaway on Earth are not present in any near-term scenario that standard climate models examine. This is not the uncomfortable finding. The uncomfortable finding is more subtle and more durable. The uncomfortable finding is that Earth's long-term habitability is not guaranteed by any physical law. It is maintained by a specific, dynamic, interacting set of geological, atmospheric, chemical, and, on Earth, biological processes that together constitute what might be called a planetary life support system. And that system, like any complex system operating far from equilibrium, is not immune to perturbation. It has thresholds. It has tipping points. It has states that, once entered, are not easily exited. Venus shows us what one of those states looks like, not as a theoretical possibility, as an actual planet sitting 41 million kilometers from Earth at closest approach, spinning slowly backwards in the permanent aftermath of having crossed a threshold that its particular configuration of variables could not prevent. The question is not whether Earth will become Venus. The question, the real, scientifically honest question, is what we understand about the conditions that keep Earth from becoming Venus, and whether that understanding is sufficient. There is a framework in Earth system science called planetary boundaries, developed by Johann Rockström and his colleagues, and first published in 2009 in the journal Nature. The framework identifies 9 Earth system processes, including climate change, the integrity of the biosphere, the freshwater cycle, and the chemical composition of the atmosphere, that together define the operating space within which human civilization has developed. Each process has a boundary, a threshold beyond which the perturbation of that process risks triggering nonlinear changes in Earth's overall system state, changes that may be difficult or impossible to reverse. The planetary boundaries framework is not a model of Venus. It is not a geological timescale analysis of solar luminosity increase or the carbon silicate cycle. It operates on human timescales, and the boundaries it defines are relevant to human civilization rather than to the multi-billion-year evolution of a planetary climate. But the conceptual structure it embodies, the idea that Earth's system has boundaries, that those boundaries represent thresholds rather than gradients, and that crossing them risks transitions to qualitatively different states, is deeply consistent with what Venus tells us about planetary climate dynamics. Venus crossed boundaries, not the same boundaries, not on the same timescales, but the architecture of the situation, a stable planetary system with thresholds that, once crossed, lead to irreversible transitions, is the same architecture that the story of Venus describes. The lesson of Venus is not specific to Venus. It is a lesson about complex systems operating near thresholds, about the difference between a stable state and a stable seeming state, about the gap between a system that is robust and a system that has not yet been pushed hard enough to reveal its brittleness. Return for a moment to the retrograde rotation. It is still there. Venus is still spinning backwards, slowly, with its 243-day day, rising sun in the west, setting sun in the east. The atmospheric tide is still operating, the sun's gravity still pulling on the massive bulge of superheated carbon dioxide. The equilibrium between solid tidal friction and atmospheric tidal torque still holding at the same improbable, stable backwards rotational state it has occupied for hundreds of millions of years. There is something worth contemplating in the persistence of that rotation, in the fact that the equilibrium Venus reached after its climate catastrophe is not temporary. It is stable. The planet is not slowly recovering. It is not trending back toward its earlier, habitable state. It has settled into the new configuration, the post-catastrophe configuration, with a physical completeness that allows no natural mechanism for reversal. The tidal equilibrium, once established, self-reinforces. The thick atmosphere maintains the atmospheric tide. The atmospheric tide maintains the rotational state. The rotational state contributes to the atmospheric circulation patterns that maintain the thick atmosphere. Everything locks together. The catastrophe does not merely happen. It arrives, and then it stays. This is perhaps the most sobering aspect of Venus's story. Not the catastrophe itself, dramatic as it was, but the permanence of its aftermath. The universe does not distinguish between a state that is good for life and a state that is not. It simply finds equilibria and maintains them. Venus is in an equilibrium. It is a terrible one, from the perspective of biology. But the physical universe does not have a perspective. It has dynamics, and the dynamics of Venus have settled. The 4.5 billion year history of the solar system contains, so far as we can determine, at least one world that made a one-way transition from habitability to permanent inhospitability. Possibly more. Mars tells its own story of lost oceans and vanished atmosphere, though through different mechanisms and different timescales. But Venus is the most striking case, and the most relevant to Earth, precisely because it began so close to what Earth is. The missions that are coming, Da Vinci, Veritas, and Vision, will attempt to read the record that Venus's surface and atmosphere still contain. They will probe the atmospheric chemistry for chemical disequilibria that might speak to the planet's past or to unexpected present processes. They will map the surface geology at resolutions sufficient to look for ancient continental structures, fossilized coastlines, the chemical signatures of evaporated oceans. They will attempt to characterize the atmospheric dynamics well enough to test the competing models of how the retrograde rotation was established and maintained. These are not missions of idle curiosity. They are, in a very real sense, forensic investigations. The crime scene is a planet. The crime, if that is the right word for a natural process operating without intent, is the destruction of a habitable world, and the evidence, buried under hundreds of millions of years of volcanic resurfacing and atmospheric processing, may still be there in recoverable form. What scientists hope to extract from that evidence goes beyond Venus. The goal is to understand the mechanisms of habitability loss with enough precision and enough detail that the findings can be generalized, applied to the growing catalog of exoplanets that the James Webb Space Telescope and its successors are beginning to characterize. Because Venus is not the only world in the universe at the inner edge of a habitable zone, it is not the only world with a thick atmosphere and a rocky surface and an orbital distance that puts it at risk. There are, by current estimates, hundreds of millions of Venus-like worlds in the Milky Way alone. Each of them is a potential outcome space for the questions this story has been asking. Each of them is either a world that managed to remain habitable despite its position, or a world that crossed the threshold and did not come back. And the frequency of each outcome, the ratio of surviving habitable worlds to catastrophically transitioned dead ones, is a number that we do not yet know, a number that has profound implications for how we understand the distribution of life in the universe. If Venus-like worlds almost always survive, if the specific configuration of factors that maintained Earth's habitability is common, and the catastrophe that overtook Venus is rare, then the universe is likely rich with habitable worlds. And Venus was an unlucky exception. If Venus-like worlds almost always undergo the same transition that Venus did, if the conditions that allow a world to remain habitable at the inner edge of a habitable zone are rare, and Earth is the exception, then the universe may be far emptier of living worlds than optimism suggests. We do not know which of these is closer to the truth. Venus is one data point, Earth is another. The exoplanet atmospheres that JWST is beginning to characterize will eventually provide more, but the science of comparative habitability is, in 2025, still a discipline building its empirical foundation. The generalizations are coming. They are not yet secure. Come back to the beginning, one last time. A planet formed 4.5 billion years ago from the same cloud of gas and dust as Earth. It inherited the same rotational momentum from the same collapsing nebula. It grew, condensed, differentiated into a rocky world with a metal core and a silicate mantle, covered in oceans of liquid water, warmed by a young star to temperatures that would have felt recognizable. And for billions of years, for a span of time that dwarfs the entire history of complex life on Earth, it simply existed, a planet in equilibrium, a world in the world-bearing region of its star's neighborhood. And then the equilibrium broke, slowly at first, then irreversibly. The oceans vanished, the atmosphere transformed, the surface baked, the rotation, over hundreds of millions of years, reversed. The world that exists today, the one that burns in the evening sky with a brightness that has inspired poetry and mythology and navigational mathematics across every human culture that has ever looked up, is not the world that was there in the beginning. It is what replaced it, the aftermath, the stable, permanent, physics-constrained equilibrium that the universe settled into after the habitability was gone. And Venus does not know this. That is, in the most strictly accurate sense, the answer to every question this story has asked. Venus does not know it was habitable. It does not know it crossed a threshold. It does not know it spins backwards, or that the spin is the record of its own catastrophe. It is simply a planet doing what planets do, following the physics, maintaining the equilibrium, carrying the history without reading it. We are the ones who read it. We are the ones for whom the retrograde spin and the thick atmosphere and the possible ancient oceans have meaning, because we are the ones standing on the other outcome, looking across the narrow astronomical distance that separates our world from that one, asking what the difference is and why it matters. The question behind the question, the one that Venus has been waiting in its slow backwards rotation to pose, is not why it spins in the opposite direction. That is the surface. That is where the curiosity begins. The question behind it is whether we understand what we have and how we have it, and how long the having of it is something we can rely on. It is a question that the universe does not answer on our behalf. It does not lean toward our survival or away from it. It offers physics and chemistry and geological time and the example of worlds that went differently, and it waits, and Venus spins on, slowly, backwards, patient beyond the capacity of any human timescale to fully absorb. A monument to the fact that the conditions for life are not the default state of the universe. They are an achievement of circumstances, of specific variables, aligning in specific ways across specific timescales, that the universe produces, where it produces it at all, without any particular guarantee of how long it intends to last. The mystery of why Venus spins backwards has no single, clean, final answer. It has a web of interconnected answers, each one opening onto a larger question, each question connecting to a story about climate and time and life and the fragility of conditions that, from the inside of them, can feel permanent. They are not permanent. Venus is the proof of that. 41 million kilometers away, at closest approach, turning slowly in the dark, the sun rising in its west and setting in its east, the sulfuric acid clouds burning bright in telescopes and spacecraft and the imaginations of everyone who has ever learned what is actually happening behind that beautiful, unwavering point of light. The universe is stranger than it looks from here, and it looks, from Venus, completely different.